G'day, my name is Jacob Carter. I'm here presenting my Statistics for Decision Making project, analysing the relationship between latitude and solar exposure. So essentially the basic science underpinning the analysis is that direct sunlight is more concentrated than indirect sunlight.
Using a flashlight, you can see for yourself that direct rays are concentrated on a smaller area than slanted rays. This is why direct rays produce more heat.
So somewhere like the equator that's pretty consistently tilted towards the sun would receive more solar exposure than somewhere closer to the poles that spends a lot of time tilted away, receiving indirect sunlight. So I'm hypothesizing, based off that, a negative relationship between latitude and solar exposure. And there's two questions really guiding this study. That is whether there's been any changes in this relationship in any given season between 2013 and 2018. And across any given year, are there similarities or otherwise between the seasons? So why is this important? Solar exposure mainly affects agriculture. Things like monitoring plant growth, irrigation, calculation of water requirements for crops. So really we're looking to deepen our current understanding of this to aid decision making in these fields. Also, to a lesser extent, solar exposure affects engineering sectors and research. 865 latitude and solar exposure measurements were sourced from the Bureau of Meteorology. They were taken from 12 locations across Australia, which were selected through stratified randomisation to ensure diversity in latitude. So to begin, it was first important to establish the relationship between the variables. Winter and autumn appeared linear, but there was a slight curve to summer and spring. This implied maybe a quadratic relationship. If this was the case, it's more than likely that winter and autumn were also quadratic, potentially just sort of occupying a seemingly linear segment of the parabola. So to confirm, we fit a linear line of best fit and a quadratic line of best fit to each season of 2013. The quadratic lines consistently gave better coefficient of determinations and the residual plots appeared more random. So we continued the analysis assuming that the relationship was quadratic. To analyse variance in the relationship between latitude and solar exposure in a given season, we calculated the quadratic line of best fit for each year, plotted those trend lines on top of each other. First one that we started with was summer, and these trend lines didn't appear as expected at all, really. They hardly supported the hypothesis. Curiously, you can see that there's a positive relationship in the lower latitudes that peaks midway through that trend line at around 27.5 degrees before it begins to curve back down and that hypothesized negative relationship becomes apparent. So this was interesting, did not support our hypothesis, but at this point I was not sure if this was a trend, if this was consistent across seasons, or if this was something maybe unique to summer. That upward trend in the first half really mitigates any average gradient, but even if you were to just consider that declining trend in the second half, the average gradient still wouldn't be very steep. This implies that solar exposure in summer is not showing a great deal of sensitivity to change in latitude. Despite this, we still managed to get a respectable coefficient of determination of 0.69, but still 30% of variations unaccounted for. So in terms of change across time, summer showed the most variance. You can see lower measures of solar exposure for the lower altitudes in 2014 and 15, and slightly higher measures of solar exposure in higher altitudes in 2013, 14 and 15. Still, overall, there is a degree of consistency though. This is backed up by the yearly trend plot, which showed no consistent increase or decrease over time. Next up was autumn, and this plot far more closely resembled what we were expecting to see. There's very little variation between the years, especially when compared to the results of summer. Additionally, there's quite a decent gradient showing solar exposure's sensitivity to change in latitude during autumn. On top of this, we have a very strong R² of 0.97, and the yearly trend plot shows no consistent increase or decrease over the 6-year time span. So already we're starting to see consistency in a given season across time and variance between seasons. There is remarkably little variance in the trend lines across time in winter, and again a yearly trend plot showing no consistent increase or decrease in solar exposure from year to year. Additionally, we have an even steeper average gradient than what we saw in autumn and an even greater coefficient of determination, 0.99. These results are further solidifying the fact that there's very little variance in a given season across time, but we are learning that interseasonal differences definitely do exist. It appears that the further away we are tilted from the sun, the better latitude is as a predictor of solar exposure, and the more sensitive solar exposure is to change in latitude. And lastly, there was spring. Spring provided further credence to our developing understanding of the relationship between the two variables. Again, we see little variance across time, more or less just a tighter arc in 2013. This tighter arc resulted in slightly less solar exposure in lower and higher altitudes. As the lower altitudes once again begin to tilt away from the sun, we see quite a mellow average gradient depicting solar exposures lessening sensitivity to latitude. When we plot the average seasonal trend lines together, the interseasonal variation becomes quite clear. Firstly, it's hard not to immediately notice that summer's symmetrical trend line is an abnormality. It appears that in summer, in locations with a latitude of less than 27 degrees, there is an additional variable limiting solar exposure. This variable's influence grows stronger the closer we get to the equator. Currently, our best hypothesis is that the variable is uniquely associated with summer in more tropical climate zones. Beyond this, based off our established understanding of the relationship, there's really no unexplained variation. It appears that winter at any given latitude receives less solar exposure than the same latitude in autumn, which receives less solar exposure than the same latitude in spring. Summer struggles to fit in here because of its unique trend line, but this simply appears to be a consequence of the degree to which the southern hemisphere is tilted towards or away from the sun. The average gradient, and therefore solar exposure's sensitivity to change in latitude, is also evident here. We can see that over the same change in x, winter has a change in y of approximately 13, whereas autumn has a change in y of approximately 11, and spring has an approximate change in y of 9. Again, summer struggles to fit in due to the influence of an extraneous variable, however the average gradient would appear to be close to zero. To summarise, the predicted negative relationship between latitude and solar exposure held up under scrutiny, the only exception being during summer, where we now hypothesize that some feature of a tropical climate zone summer mitigates latitude's influence on solar exposure. We found very little variation in a given season over time, however there was a higher degree of variation in summer, perhaps again due to the influence of the extraneous variable. Interseasonal variation, however, was evident. The degree to which the southern hemisphere is tilted towards or away from the sun, which is reflected in the season, primarily influences solar exposure's sensitivity to a change in latitude, and additionally, to a lesser extent, influences the reliability of latitude as a predictor of solar exposure.